Our next application is the Chinese postman problem. It is called the Chinese postman problem because it was solved by Guan Meigu, who was a Chinese scientist. Uh, it applies to postmen of all nationalities, of course. It's also known as the route inspection problem. So the idea is that you have a city, and either you have a person who wants to distribute mail or a person who wants to inspect the quality of the streets. In both cases, the person has to go through all the streets in the city and come back to the post office where they started or whatnot. So the question is, how can I do this most efficiently? The application for this is in, well, mail delivery, road inspections, and there are other more practical applications. And the mathematical model is that you want to look at a weighted graph, and you want to find the shortest closed trail that contains all the edges. So, for example, if your city looks like this, and you want to start here, and the length is 5, 3, 6, and 4 maybe, well, then you can go either clockwise or counterclockwise. You have one such route. So the point is that there is no escape from going through all the edges. This you have to do. So why is this a problem? Well, not all cities look like this. Maybe your city looks like that. Maybe this has length 2. So now how do I do this? If I go like this, say, and back, now I haven't delivered mail to people who live along this street, so I have to go this street out again. But then I have to go some path twice, right? I can either go the same street back, which would be shorter. So then I would have to repeat this path. Since we have talked about these things, we can formulate this in terms of Euler trace. So if your graph is Eulerian, meaning that there is a way to go through all edges exactly once, then you're lucky. Then you do that and you're done. But if your graph is not Eulerian, then you run into the problem of possibly having to go through some streets twice, more than once. So this is, for an Eulerian graph, this problem is trivial. You just find an Euler trail. We have gone through an algorithm for that. But the problem is not trivial when the graph is not Eulerian. So what do we want to do? Well, if you have a non-Eulerian graph, like this one, say, well, you can maybe make it Eulerian by building new edges, but as a postman, you don't have the authority to build new roads. You have to walk longer. You have to double some edges. So mathematically speaking, what I would do is I would write one edge as a double edge, not meaning that I built an extra road, but meaning that I go forward once and backwards once. Now I have an Eulerian graph, so now I have an Euler trail. And the point is, I want to double roads or edges that give me the smallest possible added weight. So if I'm a mailman and I have the choice of going twice along a road that's 1 kilometer and going twice along the road that's 17 kilometers, then I would ideally want my route, if I have to walk along any street twice, I'd rather it be the 1 kilometer street than the 17 kilometer street. So hopefully you have some intuition for the problem now. How do we solve this? So how do I find such a minimal weight subset of edges that if I can double them, I will be fine? In general, if you imagine a huge graph, this is difficult, but there is an efficient solution. Still, it's a complicated solution. We will not go through this, but I will give you the rough idea without any proof. And for that idea, we will have to introduce a new concept. If this is difficult, you can just skim over it. We will see a more concrete example on the next slide, which is more important. But to give you the general idea, so what is the problem in your graph? The problem in your graph is that it's not Eulerian. What causes a graph not to be Eulerian? Vertices of odd degree. So call the set of such vertices T. So this is the set of our problematic vertices of odd degree. So if my graph, say, looks like this, then all vertices have odd degree. So T consists of all vertices. But if my graph looks differently, it will be a different set. Now, I want to construct the following, what is called a T-joint. What's a T-joint? It's a set of edges so that these odd degree vertices are incident to an odd number of edges from this set J, and the other vertices that are not in T, so the vertices that have even degree, they will be incident to an even number of edges, J. So if I take my edges in J and draw them double, what will I achieve? Well, the odd degree vertices will have an odd number to add to their degrees, so they will have an even number, and the even number vertices will have an even number added to their degree, so they will still have even degree. So now all vertices have even degree, and my graph assumed connected, otherwise the problem is pointless. Now my graph is Eulerian. So in the graph that I drew on the last slide, that was exactly what we did. We had this graph, my T were these two vertices. These had odd degree, and now I added this one edge, meaning that I made the edge that was already between them into a double edge. Now I have an Eulerian graph. So now I have such a trail. And the difficulty is to find a T-joint with the smallest possible weight, and then you can double the edges so you get your Eulerian graph. And because your joint had smallest possible weight, this will be the best possible Eulerian graph. But to find such a joint in general, if you have, imagine a graph with 10,000 vertices of whom 4,000 have odd degree, this is difficult. So we will not do that. So this business of T-joints, not only is it abstract and a bit complicated to grasp, but in general, it's difficult to find an efficient way to implement it. But we'll look at a special case that will both capture the idea and refer the problem back to a problem we have already solved. And that's the case of a semi-Eulerian graph. So if you remember the case I drew on the last page where we just had to double one edge, that graph was semi-Eulerian, and that is how it worked. So let's look at a more complicated case. So this graph is semi-Eulerian. The only troublesome edges are these edges that are labeled A and B. They have degree 3. All other vertices have even degree. Of course, ideally, I would want to build an edge between these two vertices, but as a postman, I can't do that. So I have to find some set of edges that connect these two vertices in the most efficient possible way. In other words, I want to find the shortest path between A and B. If I find the shortest path, so in this case, I think the shortest path, but you have to check this, that a shortest path, I shouldn't say the shortest path, there might be several, but if I'm not mistaken, this is a shortest path. It has length 13 from A to B. So what I do, I double these edges. So now I have another edge of length 6, another edge of length 4, and another edge of length 3. Why do they get the same length? Well, remember, the problem I want to solve is, what does doubling the edge mean? Doubling the edge means that I go back and forth along the same street. And of course, if a street is 6 kilometers long, it's going to be 6 kilometers long every time I go through it. Now this graph with these 3 additional edges is Eulerian. And because this is a shortest path, then this will be the most efficient way. I'm not proving this, but this is hopefully at least plausible and makes sense, that if I find the shortest path, then adding this shortest path, I will get my solution. Because now I get an Eulerian graph, I can traverse all the edges exactly once, which means that the only roads in practice that I am doubling are these ones with 6, 4, and 3. So I'm adding 13 kilometers to the length of my route, but that's the best possible if I want to go through all routes and come back to the point where I started. Why does it have to be a path? If it's not a path, if it's a walk that maybe I go from B here and then I go this longer thing and back, and then my longer walk will include unnecessary cycles. So this is why it's enough to consider a path, and the path will give me the best possible way, provided that it is a shortest path. And we have already a way to find shortest paths, namely the Dijkstra algorithm. So by solving that, I will be able to solve the Chinese postman problem for semi-Eulerian graphs. Our final problem, and perhaps the most famous one, and also the most difficult one, so we will barely touch upon it, is the so-called traveling salesman problem. That's how it's called. There is no reason why the salesman or the postman, the previous problem, has to be a man. But so we have a salesperson or a merchant who wants to visit a number of cities to sell their product. So they want to do it in the most efficient way and come back to where they started. And this has applications in logistics. So if you actually want to construct routes between cities, when you construct small microchips, you want somehow the information to go the shortest possible way, and so on. So what is the mathematical model for this? It's you want to find the shortest, meaning least weight, Hamilton cycle in a complete weighted graph. So why is the graph complete? Well, you assume that there are roads between all the cities, or direct flight paths, or railroads, or whatever, and you just have to pick the shortest one. And why Hamiltonian? Well, because you want to visit each city exactly once. Because the graph is complete, as we saw in the problem-solving session, this is always possible. So in a complete graph, there is always a Hamiltonian cycle. For example, this one. But this one was probably not the one of least weight or shortest length. So how do you solve this to find the Hamilton cycle with shortest length? Easy. Just look at all possible Hamilton cycles. I mean, how many can there be? Calculate their lengths, write them in a list, and choose the shortest one. Well, if your graph has 4 vertices, that's not a huge problem. But in general, there are n minus 1 factorial half possibilities. If n is any number you would find in real life, like 1,000 factorial is a huge number. So this is extremely non-efficient. And if you want to ideally not sit yourself and calculate this, but program a computer, it would take immense time. In fact, it would take immense time even if you sit and calculate it by hand. So this is not an efficient algorithm. There are efficient approximate algorithms that give you approximately the shortest path with some error. You can look at that if you're interested. But the purpose of bringing up this problem is just showing you that Hamiltonian cycles and Hamiltonian graphs have an application, and this is probably one of the most famous graph theory related applications there is.